on a daily basis is the first part here. AI techniques will replace humans in problem solving. For example, your doctor may not be a doctor anymore. It might be an AI. Another thing which is not so visible is that AI techniques are now entering the sciences in general and replacing standard algorithms. And this is incredibly important and is really changing the way we do things right now. Here's a list of issues for which AI could be replacing humans, and actually are. I'm going to make a couple of examples. This is a highly incomplete list, and I haven't put them in any favorite priority. Self-driving cars, absolutely. You know, there's a big competition now. How can you actually get the first self-driving vehicle? Automated diagnosis in medicine is a particular thing that I'm going to be talking about, and this is has potential huge implications, which is, of course, just a specific subcase of the automated decision processes. If you're talking about safety and security, automatic weapon system is of interest. This is a big part of the ethical debate these days, and you have potentially seen on your devices already security systems based on face and voice recognition. What you may not have seen is the new era of AI, for example, in MRI, which I'm going to talk about in general. This is not so visible. You don't see what is happening under the hood in an MRI machine. We're not there yet, but it could happen that the next generation of MRI machines will use deep learning and AI techniques. Microscopy, you've already seen a beautiful talk on this, huge. These we can simply say imaging problems in general. Now, if you talk about security and safety, the military could get interested. And if you apply this to radar and sonar, security and safety is going to be crucial. And these are essentially all problems that I can fit into one big pool of problems, namely inverse problems, which I'm going to be talking about. I'm also going to mention PDEs. I'm not a PDE guy, but deep learning and AI has already entered the PDE field. Let me just say a little bit about neural networks. If you don't know anything about neural networks, that's completely fine. This talk will be sort of broad perspective on it. If you know a lot of neural networks, that's fine. I would like to define it, what I mean by it. NN stands for neural networks. This capital N here is going to be the vector of inner dimensions. And what I mean by a neural network is simply a composition of these affine mappings that is split with some nonlinearity in between. This is sort of the conservative mathematician's definition of a neural net. There are more general definitions out there, but for the theorems that I'm going to show you, this has no impact. I'm going to show you positive results on this restrictive class, and all the negative results are going to fall for whatever you would like to define. So this is just for the notation. Right. So with all the buzz going on, what could go wrong? So I'm going to first start asking the question, what could go wrong when AI replaces humans in problem-solving tasks? And I'm going to start with this. This is an historic document. This is the first example of a federal agency, this is the American FDA, that approves deep learning for automatic diagnosis in medicine without any influence of a clinician. This is now actually not science fiction. It's old news. Look at the date, April 11th. This is for automatic diagnosis or the automatic detection of diabetes. The way this works is that if you are diabetic, your high blood sugar level will cause the blood vessels on the inside of your eye and the retina to be damaged. And that can be essentially detected by a photograph and a neural network. So this is what they do. They train a neural network simply by looking at your retina, and it says, you have diabetes, yes or no. The way this is done, you have 900 trials. The neural net gets a score. The doctor gets a score. The score of the neural network matches almost the doctor. You're good to go. This is now, hopefully, or we'll see in the future, actually implemented for commercial use. It's at least approved. So with this, there's a whole lot of opportunities, but what on earth could go wrong? So I'm going to start with this paper here. This paper here is not written by grumpy mathematicians like myself. It is written by medical people. Isaac Cohen, who's running the project, is a very big fish at Harvard Medical School. And what you also should make notice of is that this is published in Science and pretty recently. I'm not going to read through the abstract. I'm going to try to give you the full overview of what the point of this paper is. And I'm going to do that by showing you this figure here. In this case here, they take the example of the automatic diagnosis with a diabetes as an example. But they pimp this up a little bit and say, now it is not about diagnosis of diabetes, but cancer diagnosis. More life or death, more serious. You have a mole. And the question is this benign or malignant? You do exactly the same thing. You train a neural network to decide, is this good or is it bad? And it becomes highly successful. And now you try a little experiment. You add a tiny little bit of noise. The noise is so small that the human eye cannot see it. And it goes from having very, very strong confidence this is benign to having very, very strong confidence that this is malignant. The question now is, of course, what is going on? For me as a mathematician, the question is, what did the neural network actually learn? Because the reasoning that a doctor would have saying that the anatomy here and the shape and yada yada, that's going to be basing my decision. Well, to a doctor, that and that is the same image. What did the neural network learn? What does it base a conclusion on? Right? They take another example, you can simply take a rotation. You get a wrong answer. They show examples where you take a text analysis, you replace a couple of synonyms, and you go from high to low risk. Similar, you do this in an experiment where they say this could, for example, be an insurance claim. It goes from denied to approved simply by tiny small changes. And now things become a little interesting. So the important thing is that this is not essentially the mathematician complaining. These are medical people. And you should all read the paper. It's very fascinating. And they really turn the volume up to 11. They end the paper with not, oh, these are potential issues. They say the question is when and how to interfere. So this is something that they take seriously. The mathematical question for me is, what is happening? Now, there's a whole lot of numerical experiments out there that tries to explain what on earth do the neural networks actually capture. And this is one of my favorite examples. I'm going to show several ones, for which you take a neural network that's successful, and then you show it nonsensical images. And it would have been okay if you get a very low confidence level on this. But all of these images here have 99.9% confidence level that it hits. This, to me, is maybe not a cheetah. The question is, what on earth did the neural network learn? Because it has no idea what a cheetah is, clearly. I'm going to get back to this a little later on. What this here is about is really what I call universal instability phenomenon in deep learning. And there's now a vast literature on this. You can Google adversarial attacks on deep learning, and you see it floods your search engine. Here's one particular software that I love. This is called DeepFool. It's created here at EPFL. I just want to say, I just didn't put this here because I'm here today. If you see talks that I gave elsewhere, I always have this slide because I really like it. It's great work. What these guys did was essentially to show the following. You could add perturbations like these to the images. And not only one particular perturbation for each image, but a universal one. So you take a successful neural network, and you can add one type of perturbation to all images, and then your success rate, or sorry, your failure rate goes from 3% to 90%. So what you see here is what they created, different types of universal perturbations for some of the famous nets that have been winning the ImageNet competition. Here is an example of how that would actually look. All of these are images for which the perturbation is added. You cannot see the difference, can you? It's clear that this is a Christmas sock, not an Indian elephant, right? Very clear. What on earth did the neural network learn? So, how do they do this? It's simply an instability test. If you have a neural network that could, say, recognize a cat, what you're trying to do is that you write them an optimization problem. So you try to add a little perturbation and see if that throws you off the decision boundary. So the key is the smallest perturbation that's going to throw you off. So this is an adversarial attack, if you will. I'm trying to harm and see what is the worst case scenario. And that's what they do. I'm not going to get into the details how they actually do it, but this is the bottom line. Right. So there's tons of software out there that does these attacks. The mathematical problem for me is, first of all, figuring out what's going on. But before I'm going to ask that question, I would like to ask, is this something that you should expect? Simply from a mathematical point of view, should you expect seeing instabilities in deep learning? And here's a mathematical theorem that describes exactly this. There's uncountably many types of classification problems for which you'll have exactly this. And here's important. This class exists, and then you can choose whatever power of your neural network. The dimension can be as big as you want. That does not restrict this, right? So choose the most powerful neural network that you have. This will happen. Choose your epsilon. This is going to be the instability parameter. That can be as small as you want. It must be less than 1 over k plus m. K is going to be the size of the training set, and m is going to be the size of your test set. M has to be finite, but can be arbitrarily large, 10 to the 80 if you want. Now what's going to happen is that there's uncountably many different training sets and classification or test sets. So if you train your neural network, you get your minimizer here. What will happen now is that you will have incredible success, 100% success rate on your training data and your test data. Fantastic. But you will also have ridiculous instabilities. In particular, for this epsilon, that could have been arbitrarily small, there is now uncountably many cases that are just epsilon away from your training data. Your neural network has seen this, that much away from what you're throwing in, and it gives you the wrong answer. This is exactly what you see in practice. Fantastic performance and ridiculous instabilities. This is not the paradox. Now comes the paradox. The guy that you train gives you the instability, but there does exist another neural network out there which is as accurate, has 100% success rate on the same thing, and is stable. This has nothing to do with the lack of power of neural networks. It is the way we train them. And the big question is, can you find an algorithm that gives you the good guy? That's the paradox. So we have the ones that we train, and they become unstable, but there exists a good guy. I don't know how I can get it. And I don't even know if it is possible to get it. I'm going to get back to that at the very end. Right. So if you're new to deep learning and you see these kinds of things, you may ask, do you really know what you're doing, Anders? And I just want to say that this is up for debate, and it is a part of the debate now. Some of you may know what happened at NIPS 2017 when Ali Rahimi, and in his acceptance speech for the Test of Time Award, likened modern machine learning and deep learning to alchemy. And his point was this, that alchemists essentially would take yellow and green, stir it, and hopefully, or they would try to make gold, and they wouldn't be able to do that, and they wouldn't be able to know that they couldn't create gold. Not everybody agrees with this. I encourage everybody to take a look at the debate afterwards, which is quite feisty and very interesting. I should also mention that the National Academy of Sciences in the US, as a result of this, decided to have a workshop called The Science of Deep Learning, which they organized last spring. So this did have some impact. Anyway, despite some of the pessimism, there is also great optimism. And some people do give advice on how we should educate people in the medical professions. Whether or not that's a good idea, I think that's an open problem. But what I'm interested in as a mathematician is, what does the neural network actually learn? And I cannot prove it, but I can come up with a conjecture. And this conjecture is somewhat provocative. It seems that it's us and a group at MIT who shares this kind of view. And the conjecture is as follows. Both the success and the instabilities of deep learning is caused by the same phenomenon. Deep learning actually does not capture the structure that we're interested in. It captures a false structure. This false structure is fundamentally unstable. There's nothing wrong with the neural network. It is what it actually learns that is the issue. This false structure that is completely unstable does correlate very well, and hence you get the good success that we're interested in. But it's fundamentally unstable, and the reason why we're getting this false structure is that it's much simpler with fewer data, and in the process that we train, we're capturing the false structure. And I'm going to try to back this up. I won't be able to prove this mathematically, but I'm betting an awful lot of money that this here is the case. I'm going to take a very simple little thought experiment to essentially build the argument. Suppose I would like to teach you a word in a foreign language that you don't know. I'm going to teach you the word fire truck. The way I'm going to do that is that I'm going to put you in a room. I'm going to show you a bunch of images that contains fire trucks and a bunch of images that don't have fire trucks. And when you see a fire truck, you're going to hear a pleasantly sounding sound. And if there's no fire truck, you don't hear anything. But on each image, I'm going to put, where there's a fire truck, I'm going to put a blue horizontal line there as well. What happens if I run this experiment now 2,000 times? What is your interpretation of the word fire truck? Is it an actual fire truck? Is it a blue horizontal line? Is it just a horizontal line? Or is it just a line? You see, the instability properties of you now, if I'm going to test you, will depend completely on which structure you went for. If you thought it was a blue horizontal line, I could change the color a little bit, and you would be off. If you think it is a horizontal line, the color is independent, I could take a tiny little rotation. If you think it is only a line, well, I could remove the line. So the problem is, if I'm going to say anything about you being unstable, I need to figure out what did you actually learn. So I'm going to try to do this mathematically now. So I need to define what I mean by a false structure and the original structure. So this is a little mathematical, but I have to do this to make it actual mathematical. So M, that's going to be the set of images that I'm interested in, for example. And now I have a string of predicates, and you go like, why do we need the logic here? Well, this is the only way I can make this actual rigorous mathematically. So a predicate is just a statement, like the main object in this image is a fire truck, or the main object was a blue line, right? I have n plus one of them, and there's only for each element, there's a unique one that is true. All of the others are false. And then I have a function that could take my input and give me the coordinate for which this is the predicate that gives me the truth. That's the original structure. Now a false structure is almost the same thing. I have now a different set of predicates that are completely different. I also have a function that gives me the coordinates. And the point now is that they now agree on a subset T. This is essentially now where we have the fire truck and the blue line, the same area, right? And there should be, of course, an area for which they don't agree, because otherwise this would be trivial. So this is the definition of an original structure and a false structure. And I'm now going to try to essentially, I won't prove the conjecture, but try to make an argument for why this is the case. So I'm going to take a very simple example. This is very much inspired by the paper that I showed you, this deep pool paper of the group here at EPFL. And the test images that I'm going to try are very simple. I'm going to have my set M to be 32 by 32 images that have a dark background and a light stripe. And the question that I'm asking is, which direction does the stripe go? Is this a vertical or a horizontal stripe? This is an incredibly robust decision problem for humans. I will have to perturb that or rotate that dramatically to be able to get you to think that it's that, right? It's incredibly robust. So now I'm going to try to train a neural network to do this task. So first, Now I can define my original structure, light horizontal stripe, light vertical stripe, as I mentioned. And I'm going to try to see if I can get a neural network to capture that. So we train a neural network, and the neural network does very well on many cases. Yes, vertical, horizontal. But, whoops. This guy here, I have not tried an adversarial attack. I've simply taken an element which is in my subset. This element here is not that. To you, it looks like that. The question is, what did the neural network learn? It has no idea about the geometry, clearly. What did it pick up? Can you think of a false structure? I mean, there's no blue line here, but what can it be? You see, that's the problem I have when I see these examples with the cheetah. So even in this problem here, I'm going to try to figure out what's going on. So we did not learn the original structure. What did we learn? Here's what you could do. Now I'm going to look at a very specific subset of that M. This is a very specific subset of these images that have very specific color code. In the dark area here, when I have a horizontal line, I'm going to put the -A is the color code here, and then automatically I have a 1 minus A in the light part. When there's a vertical part, I have A here, and then I have a 1 plus A. So in this case here, when A is reasonably big, you will see that there is a difference. This one here should be slightly lighter than that, and that one should be slightly lighter than that one. And now, this might give you a little hint of what the false structure is, because this is the false structure. You can just simply add up the pixel values, and that will give you the decision immediately. You wouldn't have thought that that would be a false structure, would you? There's a cute little hidden false structure in this problem, for which I can now show that on this M tilde set, if I take away the set of inputs for which A is 0, that is a false structure relative to this set here. And I'm going to make the argument that this is actually what the neural network learns. So the way this is constructed now is that I've trained on a subset for which is in M tilde. And I'm also going to test on a subset here that is in M tilde. But now I'm going to take another test set for which I flip. I'm going to call that C hat. Now I flip. All the minus A's becomes plus A's. That means that the decision problem is completely flipped. And when I run the experiment now, this is exactly what you see. This is done with, I think we did 1,000 trials, random draws from this. And when I draw from the right part, absolutely. But the neural network has most likely actually learned how to add up the pixels. When I do the flipping, it is completely clueless. That was the false structure that is completely unstable. And as I said, I cannot prove this. This is like the beginning of quantum mechanics. You start with a harmonic oscillator and build yourself all the way up. And if I'll ever be able to show you what the false structure here was, I don't know. But we need to start somewhere. So this is where we're at. So that was about the instability phenomenon for classification. And the issue was what could go wrong when you essentially change or replace human tasks with AI. And now the other problem is what could go wrong if AI replaces standard algorithms in the sciences. So I'm going to start with a paper that was published in Nature in 2018. I highly recommend you to read this paper. This is a paper about using deep learning in MRI. And the message of the paper is roughly as follows. You don't really need to know the physics nor the mathematics about this. You can simply take your scanner and get measurements, and also the measurements that comes from some image, the ground truth, and train your neural network, and that's what you need. So after the paper was published, Nature Methods had a follow-up on this and wrote about it and promoted it. And the title is quite descriptive, as well as the abstract. And it says a deep learning-based approach improves the speed, accuracy, and robustness of biomedical image reconstruction. The statement about robustness is quite bold, given that we know how unstable neural nets can be. Hence, it seems to make sense that we actually test it. So here is the actual experiment that's done in the paper. And for the record, the code so we have reproduced the experiment. We got the code from them, and we even tested that everything is fine. So we sent it back. So we have essentially control that what we did on this part of the Atlantic and what was done at the other Cambridge, Massachusetts, is the same thing. So they trained a neural network to take this is the original guy. That goes into the MRI machine, gives you the measurements, and that gets now mapped to this reconstruction, which is very good. The point now is that if this is really robust, I should be able to take a tiny little perturbation here that then gets sent to the measurements, and tiny perturbations here should only give tiny perturbations there. Watch what happens. On the left-hand side, the perturbation. On the right-hand side, the effect of the perturbation. It's beyond unstable. Now, you could have asked, is this here a fundamentally unstable problem? Right? I could have cheated. I could have picked one. Now, this is doing 60% subsampling in MRI. So, yes, it's an underdetermined linear system. And here's the state-of-the-art method, just to show that this is not cheating. The state-of-the-art method, oh, sorry, I should actually, yeah. The state-of-the-art method has no problem recovering it. And, well, you see the instability. I just want to mention that the patient did not have a tattooed heart here. This was added for the effect to see how it gets deteriorated. The way this is done is very much in the spirit of this DeepFool software that I showed you. You simply try to find a worst-case scenario, a tiny little perturbation for which you either get noisy artifacts or potentially a false tumor. And that's the instability test. So doing that, it's an engineering task on its own, and it has to be done. That's what we did. And I'm not going to get into what is under the hood. What I'm interested in now is essentially trying to figure out why this happens. But before I do that, I do want to mention that this is not something that is exclusive for that particular network. This is, I would say, universal, at least if it performs reasonably well. I could, of course, make a neural network that's very stable. I could ask it to put out 0 all the time. It's not just very useful. So the key is performance and stability. This is another MRI example, the same issue. This is done with a well-known group at Imperial College London. Here's the original. This is the reconstruction. I'm going to take tiny perturbations here, and you're going to see the effect of the perturbation to the left. It's exactly the same experiment, but with a different neural network. Can you see anything happening on the left-hand side? You see, you can maybe see there's tiny little bits here. But this network here is beyond unstable. And just tiny, tiny, tiny perturbation is going to throw you off. And you may say, this part here, this is not dangerous. It's annoying. If you run this and as an experiment and you get this, the radiologist can say this is non-physical. Right. That's not the issue. The ones that are difficult, check this out, is that. Can you see the shades here? So we show this to radiologists, and they have problems saying that I cannot say if this is physical or not physical. This is the dangerous part. So if Mickey Mouse show up in your image giving you the finger, that's fine. This is bad, right? Okay, so the question now is, why do deep learning methods give you instabilities in inverse problems? And the phenomenon here is very different. It has nothing to do with fault structure. What is happening here is all about the null space. The null space of this operator here. I have now an underdetermined linear system, and I would like to recover my x from my y, right? So in mathematical terms, I have my sampling operator, sampling map. I have my domain of, say, brain images, if you want. I'm going to put a metric on that. I'm going to do this very, very general. I can look at the range. Those are going to be the measurements. I can put a metric on that as well. And then I can say something about the procedure that we're using to train these neural networks. And then I'm going to show you a theorem. The way this is done is that you're getting a training set. The training set is in the following form. You have the original guy. This is your brain image. and you can see the measurements, and then you cook up your cost function. So based on this training, you try to minimize this so that you shouldn't have a large error. In other words, you would like to get your X from the measurements, right? That's what you're aiming for. So the cost function could be just a norm, the 2 norm. That's actually what's happening in the Nature paper. But you could have umpteen different types of cost functions. But what you end up in the end is a neural network that does the following. It takes the measurements and it spits out your X almost with a little bit of an error on your training set. And this is what causes the instabilities, because of what I call the cardinal sin. The cardinal sin is for your neural network to recover something which is close to or in the null space of your operator. That's not allowed. So what the theorem says is the following. Think about X here and X prime as an image for which you have a brain tumor, and also the same image without a brain tumor. Suppose now that that brain tumor is in the null space or close to the null space of A. That means that this guy here is going to be small. If my neural network now is doing a good job on only those 2 images, so this here is small on both of them, then all hell breaks loose. Then the Lipschitz constant can be arbitrarily large depending on these numbers here. You can get a false positive, meaning that you can add a little bit of a perturbation, and then you're going to add an extra thing in the image that shouldn't be there. Or you can add a tiny little thing, and you could now suddenly remove the important part in the image. And this only happens because you're doing too well on 2 images. Think about you're doing MRI and doing 25% subsampling. The kernel of that operator now is enormous. You have tons of images for which look very much the same. Of course, there's going to be details there that aren't going to be in the null space and close to it. And if you train and you get this, that is what causes it. And none of the methods for doing these things can actually account for that. That's why you see this on a general basis. So what this theorem says is that you need some kind of kernel awareness to be able to do well and to be able to get stability in inverse problems. So if you, for example, look at compressed sensing, if you don't know what that is, that's completely fine, but it's been sort of a state-of-the-art method now in MRI. The reason why compressed sensing gives you stability is not because of magic, it's because there is an a priori knowledge about the operator. We call this the robust null space property. Taste the word, null space. It is all about understanding the null space. And when you have that null space property, if you solve this optimization problem here, you can recover, and you can recover it stably. But there's nothing magical about this. It assumes an a priori knowledge. And this is the problem, that when we do the training, we don't take that into account. And my conjecture is this: you will never ever be able to construct a well-performing and stable neural network for inverse problems unless you have prior information. The reason why I say this is that if you should essentially try to figure out if your matrix has the robust null space property, that's an NP-hard problem. I cannot prove this yet, but maybe in a year's time, I'll be showing that you cannot actually get this. You have to have a prior knowledge on what you're doing to be able to get the guaranteed stability, just like you have in compressed sensing. There's no such thing as a free lunch, but I can't prove it yet. Right, I think I have 5 more minutes. I want to address the issue of computing neural networks that do well, because the math literature is full of statements that says that there exists a neural network that's accurate and stable, and the paradox is that we don't know how to get it. And I'm going to show you bizarre things that can happen. The first thing, of course, that could happen is that there doesn't exist a neural network that can do the job. Well, if that's the case, well, I just surrender. There's no point. But if there exists a neural network that does the job, the question, can I compute it? And there's 2 things that could happen. It could be the case that there exists a neural network, but there does not exist an algorithm that can give it the network. And it could be the case that there exists a neural network, and there exists an algorithm that can do it, but the algorithm is going to take way too many samples or way too much time. It's going to be infeasible to get there. Right? I'm going to show you examples of this now, because now you think I'm nuts. And I'm going to show you this on a very simple mapping. And I do this deliberately because I don't want you to say, you construct such a bizarre thing that you will never see in practice. What I'm going to do first is going to take this classical mapping here, the basis pursuit, and I'm going to show you that you have neural nets that can approximate this mapping, and then I'm going to show you that you cannot compute it. I even going to allow me simply just a finitely many y, so that's going to be the measurements, if you will. And I'm now going to define my mapping here as a function of y, the input, simply as an element in argmin of this basis pursuit mapping. And it's not hard to show that I can choose my new parameter here, that's the noise here, and the delta here, that's going to be the actual precision that I want, that there exists a neural network that can do this for any precision. This is just standard approximation theory. So I can approximate that mapping with a neural network. But now I'm going to ask the question, can I compute it? The problem is that if you're actually going to compute, you have to write down a Turing machine that's going to do this. That means that you can only work with integer or rational numbers. If I plug in now, for example, the discrete Fourier transform, that has irrational numbers. Or if you're running floats, which you do in 99.99% of the cases, even a number like 1/3 is not stored as the pair 1, 3, it's stored as a base 2 approximation. So whatever you have and you're doing computation is always approximate. That means that the training can, at best, be some approximation to my input, some approximation to my actual mapping, and some approximation to my matrix. But of course, to any precision that you can ask for. And I'm asking the following question. If I have that as a training input set, can I find a computer that can actually give me the neural network that I know exists? And here's the answer to that question. Choose a k is an integer greater than 2. The reason why it's had to be greater than 2 is going to be evident in a second. Choose L to be any integer. That's going to be the number of samples. Choose any norm you want. Then there exists a class of well-conditioned, and I'm cheating here because I don't have time to go through all the condition numbers in optimization. Choose your favorite one. It can be bounded, and this is still true. So the theorem now says there does not exist any algorithm that takes elements from this training set that can compute the neural network that approximates phi to k correct digits in your chosen order. That does not exist. If you're a little less greedy, there does, however, exist an algorithm that can compute an approximation to a neural network with k-1 digits. But any algorithm that can do that is going to take arbitrarily long time, meaning take any number, 10 to the 80, there will be an input for which your algorithm is going to run for longer than, say, 10 to the 80 time units. If you're a little less greedy than that, you can choose your precision to be k-2. There exists an algorithm that can do that, and that requires only L samples. So not only can you not do it in general, it depends completely on the accuracy you're interested in. If I was only interested in this part here, this k greater than 2 is just to have this k-1, k-2 phenomenon, which is a little bizarre. If I only were interested in the first part, I could have made this to be 1, and I can scale everything so that it's normalized. So to sum up, the big problem is as follows. We now have a bunch of unstable neural networks out there. There is theory that suggests that there are stable and accurate neural networks, but we don't know how to get them. And there are, as you see here, cases for which there will not exist any algorithm that can actually get it. And now we're at the actual really fundamental question, because does this imply that what we have now with modern AI is a necessary artifact of instabilities? And the question is, will we be able to overcome that, or is this a natural barrier that we won't be able to do because of foundations? And that's the big question. And that's sort of homework if you're a student. And next Friday it's due. You can give it into Michael, and it will be graded over the weekend. But with that, I thank you very much for your attention.
Okay, so, you know, since he gave you lots of controversy, you're allowed also to ask questions. Yes.
So, let me ask you what might seem provocative, but is not.
Shoot.
With this definition of stability,
Yes.
how stable do you think humans are? Because in some sense, there are a series of optic illusion which I can think about,
yes,
for which maybe a neural network would think, what did that human learn?
Absolutely.
So,
yes.
how does the fact that the system can be driven unstable,
Yes.
how much is it important, or otherwise, how often does it happen?
Yes, it's a very good question. Let me actually address this immediately. So this is an excellent question. So first, regarding your question about how do I define stability, well, I would say if the human eye cannot see any difference, I would say, and the neural network gives me a different thing, I would say that that's unstable. I understand that that's not a mathematical definition because it depends on the human eye, right? But so I could completely agree. And there's actually quite a lot of work out there that has tried to say, well, here's an optical illusion. If you look at them, the dog coming to the cat, for example, it's very clear that the human eye can spot it immediately that it's been tampered on. If I show you the cases where you take the, it takes a little while to come back to, if I show you these guys, it is quite clear, right? So I agree. It's very hard to mathematically define what I mean when I compare this to human. But we can do a trial. Simply say, I ask you, and then we all think we're pretty stable, well, modulo Donald Trump, but you know, in general, we are, right? So we could do a trial, but it's a very valid question.
How would you find the worst case scenario for human?
The worst case scenario is for a human.
Yeah.
That's very hard. I totally agree. So that's very hard. But so now let's get back to so this is for the classification. Now let's do the inverse problem. Because I don't have any answer to your question about how often do they occur. And that is because I don't know the false structure yet. Because if I know the false structure, I can tell you exactly. So for the vertical and horizontal stripes, I'll tell you exactly. I can take a tiny little perturbation on 1 pixel, and it will throw you over. But I don't know in this, you know, the cheetah example, what the false structure is because it's so incredibly complicated. So for us to be able to understand that, I need to figure out what it actually learns. Getting back to this I didn't actually mention this. This is super important. The instabilities are always stable. In other words, I find a worst case scenario. There's always a ball around that for which I take any direction and it's going to mess you up. The question, I don't know the size of that ball. It can be small, but you don't have a measure zero phenomenon. So you could make the argument that what if you run this? And the test is really, do people survive? Let radiologists look at the images, but then we get a measure of it works on average. What does that actually mean? If I, as an individual, I'm interested in essentially putting me in the MRI machine, what's the likelihood of now getting a prediction? So even getting a statistical model to answer or to ask that question is up for grabs. Homework again, next Friday. So there's a whole lot of questions that I can only ask, but not answer, but they're all very good.
Hey.
Yes.
So many questions. I could,
shoot.
like,
yeah. Fire.
You want to, can I invite you?
Yeah, that'd be awesome. Very good.
I need more time, certainly, but
yes.
I was inspired by this question, and I would like to ask you so mathematics is nice because
yes.
you kind of see reality instead of, like, you know,
well, it's
human-tainted.
Yeah, it's our attempt to essentially figure out what's going on.
So,
yes.
But now I understood everything you said. That would be way too much. I understood everything you said in the context, not of neural networks versus humans. And so when you say you put the human eye as one of the fixed points to decide what stability means or not, I was very unsatisfied. So following question.
Yes.
And then you can school me on why this is wrong. But I really don't see it myself.
Yes.
If we have a glass surface and we can see through, but other people can't.
Yes.
And a person is brought in that we can see, you and me, right?
Yes.
Do you think there exists a person that comes in, says a few sentences, and I would say total asshole, and you would say potential friend?
Oh, absolutely. Yes.
Or I would say unfriendly person, untrustworthy. Is this not an instability of us?
Oh, absolutely. So I completely agree that
in the same sense that you define instability for neural networks here. in some sense.
Okay, so
Because our classification boundaries are just chosen such that if we see something that we cannot grasp it because it's not
completely
part of the set.
Completely agree. And that's so the weakness of trying to do this sort of very, very abstract things that we now is talking about, you know, human performance versus the machine that we can't quantify. I'm still sticking by my conjecture with that example because I totally agree. So we all agree that the vertical versus horizontal is completely clear.
Yes.
There can be questions, you know, somebody says something like that, you said friend and the other one says no,
and it's so beautifully
asshole.
chosen.
Yes.
Because
it
really plays with
it's those guys over there.
By whoever.
Yes.
Because it really plays with exactly what neural networks do, summing up numbers, weighted sums, and then putting it through a decision boundary.
Exactly.
Versus what we do in our experience space. So it's beautiful.
It could be the case. I'm making this up, but you know, cheetahs. The structure there is that you take all the images and you look at the the upper quadrant and you sum them up to 5, right? You know, it could be bizarre. I'm making this up, but you see, there could be structures there that we have absolutely no idea, and humans will never look at them. But the neural network can pick them up.
I don't want to stretch my time too far, but I already have the microphone. So, which fraction of the things you showed, in order to find adversarial examples, you need to know the network that does the classification?
This is very, very good. But this takes a long time. So for the for the classification problem, the adversarial cases for the classification problem is much better understood because there's been, when was the first paper on this? 2014. It's been a good 5 years on this. We are the first ones who do the instability for the inverse problem. It's a much newer thing. So you can ask about, can I see the neural network? Can I get the gradient of that? That would be one type of attack. And then you have black box attacks. I cannot see it at all. Or you can simply say, I can know the output. But I should mention these guys from EPFL, what they did, because this goes directly into that. They showed a very, very interesting phenomenon. I only told you about the experiment that they did with the universal perturbations. But what they also showed was that you could train on one neural network. So this would be the one that you optimize for one particular neural network. And then they say, you know, I'm just going to create a perturbation, but I'm going to train on a different network. So I'm going to train and get that one. And then I plug that one in. And instead of now getting 90% failure rate, they get 55. So you still, And then that means that I don't even need a black box answer from you. I could simply, so, you know, military is terrified of this. DARPA is putting a lot of money because if you can hack it like that, you can essentially, you know, wear a T-shirt that says, I'm not a terrorist, because it can throw you off. And it will be sufficient if the neural network now gives, you know, 50%. You can't use that. So there's a whole industry now to do different types of attack, yada, 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 yada. For the worst case scenarios that we do in inverse problems, I'm trying to answer the whole question, we need to know the neural network completely. That does not mean that you can't do some stuff like that, if you see what I mean. But everybody starts with, I can do the neural network, I can write down the gradient in the optimization problem. So that's what we're doing, but you can do much more stuff. But what to be done, it's, you know, future stuff.
So what I didn't understand is, if you train different neural networks on the same data and they converge to different solutions, isn't it possible to, I mean, you always assume there's one that you've trained.
Oh, no. Oh, yeah.
But what if you train 100 on the same data that converge to different parameters?
Yeah.
Isn't it possible that then there is no attack against, say, you have a majority rule, let's say?
It's a very good question. So my thesis, so first of all, there does not exist any stable neural network for the decision problem now. That's why we have this issue. If there had been one, we would be fine. So, but to your question, if my thesis is correct, if my conjecture is right, every neural network is going to get a false structure. Maybe not the same one, but a different one. They're all unstable. Right. And so my thesis is that the reason why we have the success is that neural network is essentially a poor man's AI. It's a fantastic way of taking very few data and essentially a very simple computational method to be able to capture this. And if you take away the false structure, you need tons or more computing power, tons or more data. So if you have you take 50 neural networks on the same thing with different architectures, you're going to get different kinds of false structure with slightly different instabilities. But none of them, the way we do it now, is going to give you anything that's stable.
But sure, but if you have, what I understand, so if you have 50 unstable ones,
yes,
and you put I don't quite understand your answer, and you had sort of a majority rule, like when 26 of them decide on something, that is that thing. Isn't it, if the attacks, right, have to be different for each one of them, then there is no attack.
Oh, I see. You're going to solve the problem by saying, I have 100 neural networks.
Right.
And I'm going to do it. In that case, I don't know if anybody's tried that, but please do. Absolutely. Yes. But I still believe that you're going to fail, but I can't prove it. You have to write it up, and then somebody's going to attack you. that will happen. Yes. I can tell you it doesn't work. Okay, there we go. So there's an expert in attacking over there. So, I mean, if you follow the literature now, there's an enormous amount of defense attack. You know, so the defense guys try to do this, right? And the attacker just go like this with an AK-47. And in some sense, unfortunately, the guys who are doing the attack are the ones who have the easier job. So, yeah.
It might be completely off. I am not a computer scientist, I'm an electron microscopist. Okay. And I know what we do when we do averaging, alignment and averaging of images from an electron microscope. So we usually target a certain resolution based on the magnification that we have at the microscope. Right. And we know that pixels have relevance to a certain point because we know that you can have an incredible amount of pixels, but if you know the resolution of the microscope that you can get is a certain number, then what you usually do is that you bin your data set or you filter it because you know that otherwise the stuff that you have at high resolution is irrelevant, right? Yes. So in your image where you show that the medical results can change with a minimal change that you input in the initial data set, is that minimal change relevant? Can you teach, can you somehow change the network or instruct the network on avoiding certain details because they are irrelevant for what you want to see in the final data set?
But in your case, so the crucial part here is that there's an operator. In this case here, there's the subsampled Fourier. I'm taking pure measurements that I'm doing for full sampling. And it's the null space of that operator. So if you're doing microscopy, you do actually pixel samples, this will not apply. This is, I have an operator for which there's a null space. And what I'm saying is that for you to be able to control that, you need to have an awareness of the null space. And if you're able to construct an algorithm that can do that on the spot, I don't believe that's the case. I think that when we be able to show an impossibility result. But I do think that if you have an a priori knowledge of your operator, that you can design a learning procedure. I don't know how to do it yet. So in that case, but I need to have extra information. That's my thesis. So to answer your question, I don't know how to do it. I think you can do it if you have extra information, but I don't know how, if that made any sense.
Well, the lady behind you.
Is it on?
Yes.
I was wondering if you could close the loop somehow and get the network to be self-aware of its instability by making it iterate and see if it gets different answers for small changes.
Are we talking about classification or inverse problems?
Classification. So in the sense of the patient being erroneously, randomly assigned to being ill or not.
Yes.
I think it will mean if you run the algorithm a few times for a minutely altered image and you keep getting different answers, then you know that something is wrong, so you have to try a different conclusion. You have to try a different process to get to the right conclusion.
But so in the iteration, am I doing an adversary case just to see if I'm getting a perturbation in that case?
Yeah, exactly.
Okay, so this is seems to me to describe adversarial training.
Okay.
So which is, I think now sort of the state-of-the-art defense. So there's a group at MIT that I think is sort of the leading one in adversarial training. And I think the conclusion to that is that you get a little bit of gain. But here's the interesting thing. You also lose performance. So if the thesis is correct with the false structure, that's exactly what you're doing. Because when you're essentially trying to get the correct structure. And for that, you need much more. So I cannot say that there's numerical evidence that says this is how it is. But it does suggest that that might be the case. So if you're actually trying to get what the doctor knows, that is so much more demanding. And we still don't know how to get there.
So we'll have one last one, and then actually the apéro. Okay, so we need to keep some time, and you can ask Anders as many questions as you want. Okay, so still a last one. Yeah.
So I might be wrong with the question, but I'm going to go for it anyway. So you said that to construct these adversarial examples, you need to have a null space for the operator that you learn.
Yes. I can't do this if this was full sampling. Then so everything would be fine.
In that case, is there kind of a trade-off between the accuracy of the neural network and how robust it is?
Yeah.
Let's say you have you choose lower number of features and you represent your stimuli burst, then you can have more robustness.
Well, so this is exactly hitting the nail on the head. Point is, this is a little bit like jumping when you do length jump, right? You know there's a plaque, and there's an optimal way of hitting that. If you go above it, you get the instability. If you go here, you're not going to be able to perform as well. The problem is, where is the boundary? The boundary will depend on your sampling pattern, and the boundary will depend on your class. If the class was all signals in the world, of course you're not going to be able to get any boost with deep learning. If this was specific type of images, yes. The question is, what is the boundary? The optimal mapping, we don't know. So as long as I don't know the optimal mapping, that's the key problem here. So how to be able to do that? I don't know. But my conjecture is that you need a priori information about the operator itself to be able to do it. Because otherwise you're going to be fumbling around in the dark, and sometimes you're going to go above it, and sometimes you're not going to hit it. So there are stable neural networks. Michael has created it. If you look at one of his very, very nice first papers on this, there's a network that does ellipses, and that's actually super stable. If you throw in a tiny little detail and try to reconstruct it, it washes out completely. Because these ellipses are actually, these ellipses are not in the null space of the operator he's considering. So if you compare now to another method, it's terrible because it doesn't perform well of getting small details, but it's incredibly stable. And that means that you're essentially quite far away from the optimal, if you see what I mean.
And if you show it to Sheff and Logan, it beats everyone.
Yeah, because that's super simple and has ellipses, yeah.
But let's thank the speaker again. And